Hi guys, it's Dr. Foy. This is the video that I told you about on thermochemistry and phases, and so I'm going to quickly run through chapter 5. We'll go into a little detail towards the end of it, and then the new material at the end, and in chapter 10 I'll take a little more time on. So unfortunately this diagram didn't come in very well, but you probably remember that on the top here was the idea of weather and of storms gathering energy through heat transfer, right? And then we talked down here about the gummy bear and putting the gummy bear into potassium chlorate and the significant amount of energy that came off of that. So the whole point was to talk about stored energy and release of energy, and talk about the general field of thermodynamics, where we talk about science and the heat and work component of science. So if we talk about the kind of the basics of energy, energy is that ability to do work, and remember we defined work in that variety of ways. We defined it as chemical. We defined it in terms of chemistry as heat, but then stored energy and energy of motion. And so we have to go back to this kinetic energy, which is the energy associated with motion, right? And then the potential energy, which is the energy that's called stored energy or energy of position. And that is where chemical bonds store energy, and then we get that energy back in terms of motion of particles. And then you remember the description here of the diver, right? And he's at high potential energy here, and then jumps off and goes to lower potential energy and gives off kinetic energy. But the big thing about energy is that it's conserved, right? And that's the first law of thermodynamics. So it can't be created or destroyed, it just changes from one form to another. And then this idea that we measure in terms of joules, but oftentimes you'll see it in terms of calories, and 1 calorie is 4.184 joules. Only two ways that the energy can be transferred between a system and the surroundings, and that's through heat or work. So this idea of work, right? We looked at CO2. You don't see the whole picture here, but we looked at CO2, putting it in a sealed container, the Ziploc bag, and then as it gained energy, the particles were moving faster, exerting more pressure. So there was pressure volume work that was done. And then we look at energy, and we look at delta E, okay? And in delta E, that's the change in energy, and the change in energy is equal to the heat and the work that is done. We call this internal energy because it's all the different forms of potential and kinetic in all the particles in a system. The energy, though, is really hard to determine, and so there's so many components, we try to limit these things. And so if we're interested in a change in energy, right, we can start to look at the ways in which the change can happen, and we can make it depend only on heat. So you probably haven't thought a lot about heat and temperature, but if you do, they're different, right? The temperature is actually a measure that we're aware of kind of how hot something is, right? And so we could measure the temperature of a match and measure that versus a campfire, and both of those might be the same temperature, but obviously they have different amounts of heat. So heat is not only dependent on the temperature of an object, but of the mass of the object. And the big thing that we worry about and talk about is which direction is the heat going, right? When heat is going into a system, so in other words, this cold pack is taking heat from the surroundings, that's endothermic. When heat is coming out of a system, so this flame is producing heat, then it's exothermic. So obviously these slides aren't translating well into this, but we went over this, and so we ought to be able to talk just quickly about this, right? Because the big deal was the system, right? And so if you looked at the heat transferred to the system from surroundings, right, then it could go to the system from surroundings. That Q is going to be for the system, right? The Q is going to be, that is taking on heat, so it's a plus, right? A positive, it's greater than 0. If the heat is transferred from the system to the surroundings, that's a negative. That means that heat is being given off by the system, right? Energy in the first case, it was increasing. Energy in the second case is decreasing. Work is the same thing, right? So when work is done on the system, right, that's going to be a positive W, and when work is done by the system on the surroundings, that's going to be a negative. Again, those correspond to the energy change in the system. But in chemical systems, it's more appropriate to talk about enthalpy. Enthalpy is the heat content of a substance at a constant pressure. All right. So when we talk about enthalpy, it is a state function. What does that mean? Well, it means basically that it's very difficult to measure it in either state, right? So in the initial or the final. But what you can measure is the change. And this is supposed to be delta, right? So the change in enthalpy. So the change in enthalpy, that depends only on the difference between the initial and the final. And so, again, we can find that, right, as we know what happens in terms of the transfer of heat and the transfer of heat at constant pressure, right? So now we're saying that this Q and a constant pressure is equal to delta H. Well, that means that at a constant pressure, there's no work, right? That takes the work component out. And so if we can take that work component out, then we're getting to the point where the delta H, or the enthalpy, is equal to the delta E. And that means that we are now holding everything else steady, constant, however you want to look at it, and we're only looking at enthalpy. Okay? So that means that the delta H is something that we can use to talk about these chemical reactions. So remember this, delta H, right, could be described as the heat change, right? And if we want to look at heat, we look at Q. It's pretty close to delta H, right? But in this equation now, this heat is related to the heat capacity, to the mass, and to the delta T. So we could rearrange this thing to look like this, where it says Q, the heat, is equal to C, right, the heat capacity, times M, the mass, times delta T, change in temperature. Remember, delta T is equal to T final minus T initial. All right? And then we can go down here and we can look at, okay, how do you use that equation? Well, ethanol cooling, 27.2, final was 9.8, plug everything in, and you get 7.8 kilojoules, a negative 7.8, right? These signs are critical. Heat capacity is really important, right? And recognizing the heat capacity of, or the specific heat capacity of water is really important. You're going to see this a lot in a bunch of these, and you're going to see it more likely as 4.184, right? Because that's the number that we almost always use. But recognize that all the rest of these are really small. Look at these, all less than 1, all less than 1, right? So water is an extremely important compound in terms of its capacity to absorb heat. Ethanol has some similarities, and ethanol is greater than 1 because it has what we talk about as hydrogen bonding. In other words, it holds itself together pretty well, and it can absorb heat. All right, so what can we do with this Q equals mc delta T? Well, we can look at two different systems. We can look at the system, right, within an isolated surrounding. So in other words, we can take this coffee cup calorimeter and we can create our own surroundings. So fill this thing with some water, right, and dump something in there like this iron that's hot, and then try to figure out what's going on with it, right? That's a coffee cup calorimeter. It's removing the bulk surroundings and creating the surroundings of water. And so now what you can say is that the heat lost is equal to the negative of the heat gained. And so when we know what's lost the heat, in this it says mass of iron cools, we know it's losing heat, and so we put iron on this side. And then water warms, and so we know that it's gaining, and so we put water on this side. So now we've got the Q of the iron is equal to the negative Q of the water. Plug things in that we know, right? Specific heats, masses given in the problem, temperature differentials, right? Final minus initial. Final is the same for both. That's important to recognize, right? Plug all of it in, solve, and you get this 171 grams of iron. Okay, so we talked about heat, right? We talked about the specific heat capacity and that equation. Well, remember we were trying to make the analogy of heat being pretty similar to the enthalpy or the delta H, right? So now we can kind of take another step into reactions, and we can look at reactions where we're given some kind of enthalpy change, a delta H, and then we're given a reaction, and here it is, right? The delta H of reaction in this reaction is minus 114.1 kilojoules. But what we're asked is about the decomposition reaction, which is the reverse of the reaction. If it's the reverse of the reaction, we just reverse the sign, 114.1 kilojoules, right? And it's a positive 114. And so, again, what we can say is, if we know that that's the reaction, the reverse of the one that's listed, we can say, let's find the number of moles using a molar mass. Once we use that molar mass, then we use the stoichiometry that is given in that reaction, and we find the total for that 2.45 grams. So now this brings us to Hess's law, because Hess's law now gives us ways in which we can figure out enthalpies of various reactions. So in other words, when you can combine, Hess's law says, when you can combine the reactions to get out a reaction that you're interested in, you can simply combine the delta H's, or the enthalpies. So when you look at this reaction, right, what you have to say is, how do I combine these two to get that one? Well, the way you combine them is by reversing this top one, right? If you reverse the top one, that reverses the sign right here. And once you reverse it and you cross out the things that appear on both sides, you get the reaction that you're interested in, and that means that you can add the two together and get to the minus 110.5 kilojoules. So again, these diagrams aren't coming through, but that's not a problem on this one. Again, this is just more Hess's law, right? In other words, you have these two equations at the top, and this equation as the one that you're interested in finding the delta H for, if you can figure a way, right? And the way to do it is to reverse this one. So it goes from this negative to positive, right? And then once you reverse it and you add these two together, now you get this one. Add the two delta H's together and you get this minus 43.6 kilojoules. So there are these standard enthalpies of formation. So in other words, when you have some simple reactants going to a product, in this case, you've got the actual elemental components, right, of each of these. So these are standard heats of formation, okay? They're standard molar enthalpies of formation. So in other words, they are to make a mole of this stuff, right? And so it's the formation of a mole of each of these products. So what are some important things to understand? Well, first of all, the enthalpy of formation of any element in its standard state is 0. So in other words, these guys, their formation is 0. They're in their standard state. All of these reactants in their standard state. So they're all 0. So if it's forming a solution, it's the formation of what we would call 1 molar. Okay. Most of these are negative, indicating that energy has been given off, right? So most of the delta H's are negative, meaning that it's an exothermic reaction. And the more negative it is, right, the more thermal stability it has. So it gives off a ton of heat. It's pretty stable, right, meaning that you have to put a ton of heat into it to break it down. And then these values for delta H of formation for a whole bunch of species are found in an appendix in the text. So once we've got these molar enthalpies, now what we can start to do is we can start to put together reactants and products, okay? And when we do that, we can come up with, and this equation at the bottom is buried, but the delta H of a reaction is equal to the summation of the delta H of products, the delta H of formation, okay? The delta H of formation of products minus the summation of the delta H of formation of reactants. Okay. So that means that I can look at this reaction up here and I can say, what's it take to make this? That's a reactant, C2H4. What's it take to make H2O? That's another reactant, right? H2O. So now I've got these two reactants. Well, what's it take to make this C2H5OH? Here it is. Here it is. We can put those together in this form, right, where we took the delta H of formation of the we can put this together into a form that allows us to find the formation of the products, formation of the products, formation of the reactants, right? And in any reaction, we can get to a way to find that delta H of reaction, right? So delta H of formation of products minus summation delta H of formation of products minus summation delta H of formation of reactants. All right, so here's a better representation of that equation, and this is just a zero or a degree here in all three of these, and the degree stands for standard standard enthalpy of formation. So standard meaning that it's at a particular temperature, okay, 25 degrees C. So here I've got these formation, delta H of formations of these different compounds, right? And so I have all of the compounds in this equation, and so what I can do is I can plug those into this summation, right? This summation equation, and I can take the products, CO2 and H2O, and I can take the molar quantities, this 10 and 4, and I can say, great, I know that the formation of CO2 is minus 393.5, but I have 10 moles of it, and I know its molar enthalpy, and so times 10, times 4. And then I go over to the reactant side, right? And I look at this 77.7 kilojoules for the C10H8, plug that in, and then it turns out, right, that O2 is in its standard state, so it's 0. So now, sum all these up, right, subtract out this 77.7, and we get to the standard enthalpy of the reaction, right? So now you could take this and say, well, this is naphthalene, this C10H8. So what happens when you have 12.8 grams? What's the heat of reaction? Well, I just determined the standard molar enthalpy, and there's the number of moles, right? By dividing by the molar mass, this should not be there, that 128.164. Divide by that, and you get the moles of C10H8, and then here's the molar enthalpy, right? And then we get this minus 514.9 kilojoules. So this table comes from a different book, but it's a standard enthalpy table, and so when you look in your textbook, you're going to find something very similar. And what you find is this: it says delta H of formation, the delta H, and then again that degree, meaning it's the standard enthalpy of formation. It's in kilojoules per mole. And you find these standard states at 0, right? Find these things that are in their standard state at 0, and so you already have some knowledge of this going in. You don't necessarily even have to look these up, right? All of these diatomics, they're going to be in their standard state, and then any element in its elemental form, it's going to be in its standard state, and you're going to have this 0, right? Okay, so now we're going to kind of shift gears, and we're going to start talking a little bit about phases. So phase changes, right? You know the phases: solid, liquid, gas, and the phase changes actually going from a solid to a liquid to a gas. And we're going to talk a little bit about the energy in those phase changes. So I mentioned this, the kinetic molecular theory in lecture, right? And you guys really do have a really good idea of what the kinetic molecular theory is. And the way we describe it is essentially through the motion of particles. In the solid form, right, we know that particles take their own shape. They're fairly close together, and they're not moving very rapidly. In their liquid state, they would take the shape of the container. They're starting to move a little bit more, right, so there's more kinetic motion involved here. And they have had some heat applied to them to get to that state. You apply some more heat or reduce pressure, and you can get to the gaseous state, right, where you've got a lot of movement. The particles completely fill the container, right? There are no surfaces like there are these in these liquids and solids, and they're flying around, right? There's a lot of energy of motion in there. Take away the energy, and you get to the liquid state. Take away more energy, and you get to the solid state, right? That's the kinetic molecular theory. It is the idea of the motion of particles is a measure their kinetic energy, and their kinetic energy directly determines what state they're in, what phase they're in. So if we look at a energy distribution diagram, right? That's what we're looking at here. And what you'll see is that we've got on the x-axis the kinetic energy, on the y-axis we've got the number of molecules. As you change temperature, right? As you put energy into a system, as you increase the energy, you go from low to high. This population shifts, right? It shifts from lower kinetic energy to higher kinetic energy. That also then shifts the number that have enough kinetic energy needed to escape, right? Now, what are we talking about? Well, we're talking about escape to the next phase, right? Be that from solid to liquid or liquid to gas. So let's focus a little bit on liquids for a minute, okay? They're a little bit more challenging to characterize than solids and gases. You generally don't have the order that you have in solids, right? But they're in contact with one another, and so you can't really use the ways that we describe gases, right? So we know a lot about their properties, right? But we want to be able to describe them a little bit further. One of them is called vaporization, right? And that's how does the liquid get converted into a gas, right? It goes from a liquid to a gas through this idea of vaporization. The opposite of that would be condensation. So the energy that it takes to vaporize 1 mole of liquid at its boiling point is called the enthalpy of vaporization. It's down here in this Clausius-Clapeyron equation that we'll talk about in a second, but that's that delta H of vaporization. Okay, that's that amount of energy. An identical then quantity of that energy is released when 1 mole of the same material condenses. And so the delta H of vaporization, the opposite of it is the delta H of condensation, and it's got an opposite sign. So what about this vaporization? How does it get there, right? Well, again, these pictures didn't come through very well, but fortunately this one did. Because one of the big things that you have to think about is something called vapor pressure. In other words, how much of the particles in a solution are pushing through the barrier and getting up into the gaseous state, right? How much of them is getting up into the gaseous state? And if you looked at this diagram, you would say, well, this has to be an increase in energy, and you'd be right, right? As you heat them up, more of these are getting into the gaseous state. You're increasing the vapor pressure. The pressure of that liquid, of the molecules of the liquid escaping out of the liquid, right? And so this last statement is important. It's largely dependent on temperature, okay? So there's this relationship that we can look at, and it's called the Clausius-Clapeyron equation. Okay? And the equation tells us how the vapor pressure of a material changes with temperature. Okay? So there's a constant here, there's a constant here, and then there's temperature. There's the delta H of vapor pressure, which is associated with the material. And then there's the pressure, okay? The natural log of the pressure, the ln of the pressure, right? So great, that is all very interesting. You can find the pressure at a given temperature, but what is more interesting is that you can find the pressure at different temperatures, okay? And by knowing either, knowing P1, P2, and let's say T2, and looking up the standard enthalpy of vapor pressure, you could find T1. Or knowing any of the other three and not knowing one, you could find that given one. Again, R is a constant. So one of the things that is important here, one of the things that's important here is that we can look at what we call boiling point elevation, right, or boiling point lowering, right? And so we can look at the pressure and the differences in pressure, for instance, between, let's say, sea level, which is about where York, PA is, and about where Boston, Massachusetts is. And we can look at the difference between that and a mile high in Denver. Or we could look at the difference in, sea level, Boston, and Mount Everest, right? And that actually ends up changing the boiling point of water, because the vapor pressure, so boiling point is the point at which the vapor pressure equals the external pressure, right? And so if you're at a lower pressure, right, this 0.32 atmospheres versus the 1 atmosphere at sea level, if you're at a lower pressure, then the boiling point is lower because it doesn't take as much energy to match the vapor pressure with this lowered external pressure. Okay? Same thing in Denver, where it's a little less than the 1 atmosphere at sea level, and the boiling point of water is lowered by 6 degrees. So we can do a calculation where we can figure out what the change is, right? And so we're looking at the normal boiling point of 80.1 and the enthalpy of vaporization, or the delta H of vaporization, is equal to 30.8 kilojoules per mole, right? And the boiling point of benzene, that's the normal boiling point. This is at 1 atmosphere. That's what the normal boiling point would be. But now the atmospheric pressure is 83.4 kilopascals. We'll have to do a conversion, right? And then we could plug all these things in. We've got one of the temperatures, T1. We could identify this as T1. We could identify this as P1, right? Here's P2. Here's the delta H of vapor pressure given, right? So what are we missing? T2, right? So that's the question here. Okay, so we need to also now talk about liquids, right? And when we talk about liquids, we have to talk about a boiling point. And when we think of boiling point, right, that's what we just got done talking about, because the boiling point is this point at which the vapor pressure, so the pressure on top of this liquid, the vapor pressure is equal to the atmospheric pressure. So that's this whole discussion of boiling point here, right? But when we also talk about liquids, we can talk about something called supercritical fluids. We talk about supercritical fluids. There's a point in the phase diagram, and it's missing right here. Unfortunately, we'll look at one later. I'll grab one and put it into this. But there's a point at which you get to the critical point, and that is on the phase boundary between liquids and gases. And at that critical point, you enter something called the supercritical fluid region. You can't see the liquid at that point, and you kind of can't see the gas at that point, but the properties are similar to both. Okay? The properties take on some of the characteristics of gases and some of the characteristics of liquids. It's actually very interesting, and it's used quite a bit in chemistry, particularly in our ability to look at extractions, to look at separations, things like that, where we can dissolve things in this supercritical fluid. Okay? You can't dissolve stuff in a gas. You can dissolve stuff in a liquid, but a liquid, you can't flow the liquid into tight spots. A gas, you can flow into tight spots, right? And so taking on characteristics of both gives this supercritical fluid an advantage. Okay, so this looks at what we call the phase change energy diagram. What are we looking at here, right? I mean, we're looking at what happens to something when it goes from a solid down here to a liquid up here to a gas up here. Now, the melting point is actually the point at which the energy goes up, right? The temperature goes up, and there's not as much movement in the energy. And then you have this whole point here where it's in the liquid phase, and it's just gaining energy. That would be, so Q1, right, would be the heat, the melting point. Q2 would be the heat in that state. Q3 would be the heat required to get up to the gaseous state, right? And then this line here would be a Q4, right? And that would actually be going from now the boiling point heat required, right? So this liquid's in that state for a long time. There's a lot of heat required at the boiling point for this to actually get into the gaseous phase. The Q, the energy required to do all this, is equal to each of the steps. This is another version of Hess's law. Okay, so total heat of these phase changes from solid to liquid to gas is this Q1 plus Q2 plus Q3 plus whatever steps are involved. And so now you've got heat of vaporization, you've got heat of fusion, right? And those heats are the amount of energy that must be put in during those periods. You can find those, right, using this, the Q, where you take into account the moles, right, and the delta H of vaporization or the delta H of fusion, right? So here's a better close-up picture of that curve, right? And, where each of these comes into play, right? So melting point, boiling point, right? Delta H of fusion, delta H of vaporization, right? And then this is to go from, right? This is the heat required to go from the where everything has melted and get all the way up to the boiling point. Okay, so that's this Q. Right? Right. So what affects these phase changes? Well, the biggest effect in the phase changes is intermolecular forces, forces between molecules. Okay? And so if we talk about these intermolecular forces, one of the ones that we can kind of focus in on is something called hydrogen bonding. Hydrogen bonding is an intermolecular force. It's a force between molecules. Okay? So the things that bond intermolecularly in a hydrogen bonding way are hydrogen with fluorine, right? Or oxygen, or nitrogen. The hydrogen has to be bonded directly to, right, the fluorine, or directly to the oxygen, right, or directly to the nitrogen, right? And in that case now, you set this up for hydrogen bonding because what you've created is what we call a dipole, right? That dipole means that there's a positive and a negative, partial positive, partial negative charge in this. So that partial positive, right? The partial negative would then lie on the nitrogen. Okay. Same thing here, partial positive, partial negative, partial positive, partial negative, right? That sets these things up to have interactions, right? Interactions now between molecules, between the positives and the negatives of different molecules. That's so look at how this works in ethanol, right? Ethanol has this thing that kind of looks like half of water, an OH group. And so it's got this partial positive charge on the hydrogen. It's also got a partial negative on the oxygen. These guys can cozy up and you have a hydrogen bond. The hydrogen bond is a really strong intermolecular force, but it is no match whatsoever for the intramolecular forces, okay? So covalent bonds, ionic bonds, those are between atoms. Those are the strongest. Hydrogen's bonds are not even close, but they are the strongest intermolecular forces, all right? So between molecules, between two. So that has a tremendous impact on their energy of their phases, of their phase changes, right? And so if you look at something like ethanol, we know that it's got this hydrogen bonding capability, right? Look at this boiling point. This is the same, so they're looking at the same molecular formula, but this is dimethyl ether. There's no hydrogen attached to this oxygen. So it doesn't have the capabilities. It doesn't have the hydrogen bonding capabilities. And so look at that. Minus 22 is its boiling point. Okay? So clearly there's a tremendous difference between the intermolecular forces of ethanol and dimethyl ether. again, more pictures of hydrogen bonding. Why? Because it's really important, right? You know where water, right, boils 100 degrees, right? That means that those hydrogen bonds are extremely strong. Those intermolecular forces are extremely strong, making this, um, you know, a tightly held liquid that requires a lot of energy to boil. All right, so let's just look at these, right? Let's look at these different molecules. Ethanol, what kind of intermolecular forces? Well, there's an OH group, hydrogen bonding. Ethylene glycol, there are OH groups, hydrogen bonding. Ether, no OH, no oxygen attached to a hydrogen, no hydrogen bonding. Water, hydrogen to oxygen, hydrogen bonding, right? So you could predict the boiling points of these, right? You would predict that because we know of water, this has the highest boiling point, but ethylene glycol is going to have a pretty high boiling point, right? As well as we know ethanol has a pretty high boiling point. Okay, so we're going to have to look much more closely at phase diagrams in lecture um, next Tuesday, okay, when we do some of this review. But there's just a ton of information in these phase diagrams. And the phase diagrams essentially tell you, um, where the line is going from one phase to another, and then it's pressure versus temperature. And so you're looking at how pressure impacts the phases and how temperature impacts the phases. But again, we'll do a lot more of this on Tuesday. All right? So that's it for all of this thermo and phase discussion.